Good morning, everyone. Today is the 6th. I hope you guys are having a good day. I hope everything's starting out well for you. What we are talking about today is gases. If you remember last time, what we discussed was states of matter. And I never get the SSO. Oh, well, if you never get the SSO option to join, that means you're already good. You've already authenticated your account. Or that's my interpretation. I am recording. I'm going to go full screen. Most importantly, if you don't get the SSO notification and you're here, then you're here. That's good. Um, okay, so we've got a couple of poll questions today. We're going to get through all those. Um, we were talking about gases. Now, the important thing to know about gases is that they are, well, or a gas is a state of matter. We talked about states of matter last time. We talked about solids and liquids and gases. Those are our three kind of most common and most important states of matter. Now, what's helpful to think about with gases is to connect this back to what we've talked about with respect to intermolecular forces. Now, could you tell me in the chat, is it inter, ER, or RA? Inter or intramolecular forces that are the forces between separate molecules. Inter, just add ER or RA if it's intra. Inter, perfect. Great job, Kelly. That is correct. Our intermolecular forces. Now, as a little bit of a review, when it comes to those intermolecular forces, we talked about a couple of different ones, and I'm going to rank them. I'm going to show you those ranked from basically weakest to strongest. So our weakest intermolecular forces are our dispersion forces, sometimes referred to as, or dispersion, sometimes referred to as induced dipoles. Then you have dipole-dipole forces. And I'm going to say dispersion equal sign induced dipoles. We've got dipole-dipole forces that are a little bit stronger. And then the strongest intermolecular forces that we talked about were hydrogen bonds. Now, I always like to give a little bit of a review on hydrogen bonds because I think that it's helpful. If you had two molecules of CH4, CH4, not CHY, oh, Joel, CH4, could these two molecules, if you had two CH4s, could they hydrogen bond? Give me a Y or an N in the chat. Okay, I'm getting a mixed response, some yeses, some nos. The answer is no. Now, the reason why. So I'm going to go ahead and say no H bonding. The reason why is because in order for hydrogen bonding to be present, you have to have an oxygen, nitrogen, fluorine, and a hydrogen. So I'm going to say if you had something like CH3OH, two of these molecules. Now, what that would look like would be this. So if you have an OH group in two molecules, then you're going to be able to have hydrogen bonding. If you had, so I'm going to say yes, and then if you had something like NH3, well, what does that look like? NH3, the Lewis structure of that looks a little bit like this. Could NH3 hydrogen bond? Give me a Y or an N in the chat. Absolutely. We have this, and I'm going to go ahead and switch colors to illustrate this. We have an NH bond. That could be involved in hydrogen bonding. Similarly, this could be involved in hydrogen bonding, and so could this. And so that's one of the questions that I want you to kind of be able to navigate and be able to like approach. Um, if I give you a molecule, I want you to be able to answer, does this have hydrogen bonding? Or is this capable of hydrogen bonding? So now back to CH4. Could I get a 7 in the chat if you follow why CH4 could not participate in any sort of hydrogen bonding? And any other character other than a 7 if you want me to explain that or talk about that again. Okay. So, when we talk about how molecules interact with these intermolecular forces, that's going to give you a kind of sense of, well, what is the state that this is at a given temperature? Or what state is this in? And if I were to say something like H2O versus CH4, and to think about the types of, and I'll just go ahead and say at RT or room temperature. Now, methane is CH4. At room temperature, that exists as a gas. Water, well, what does water exist at room temperature? Is it a solid, liquid, or a gas? S for solid, L for liquid, or G for gas? It's a liquid. You're absolutely right. Now, a good thought about why that is, well, because water molecules are held together through hydrogen bonds. So they have these strong interactions. CH4. CH4, well, that's a nonpolar molecule. We already know that it can't do any sort of hydrogen bonding. So CH4 isn't going to have hydrogen bonds hold those molecules together. Similarly, since it's a nonpolar molecule, you're not going to have dipole-dipole forces holding them together. So what that means is that CH4 molecules, they're going to be held together only by dispersion forces, the weakest intermolecular forces. And so they will kind of bounce all over the place in some respects. Now, with that in mind, I want you to kind of think about these things as like, okay, that's my model for a gas. Now, this right here, I'm going to get my cursor so I can grab this link. Had that one. Okay, click. I'm going to go ahead and switch my share so I can show you. This is a good illustration of what a gas looks like. All of those blue balls are representative of individual gas molecules. Now, answer in the chat. Go ahead and say Y for yes, they're all going at the same speed, or N, they're not all going at the same speed. Yeah, they're not going at the same speed. And if you're thinking, well, how do I know that? Just watch them, and there's some that it's easier to track, and then some that it's a little bit more difficult to track. The ones that are easy to track are the ones that are moving slowly. And this is all like these are moving relatively at different speeds. Now, in addition to that, their motion is super random. They hit one another, they hit the walls of the containers, and they collide with one another a lot. So this is a good illustration what a gas looks like at the molecular level. What do you think happens? And I'm going to go ahead and add the link to the chat. What do you think happens to the speed of these balls if the temperature of this gas was increased? Go ahead and do you think, does it F go faster, um, S goes slower, or they are unchanged in their speeds? Yeah, they're all going to go faster. Now, with that in mind, what do you think about the number of collisions, both with the sides of the container and with one another? What do you think is going to happen to the number of collisions? And I'll let you fill in the blank on that one. Yeah, the number of collisions are going to increase. You're absolutely right. Now, if you understand that, that's a good place to be in to understand kind of theories of gases. The specific theory of gases is, well, known as the kinetic theory of gas. or kinetic theory of gases, that their motion is related to the volume that they occupy. Now, as we proceed from here, another thing to think about when it comes to a gas is to look at how a gas behaves under different conditions. So I'm going to grab this link as well, pop this up, change my share once again. Gases intro. Okay, so we're just going to go with the intro. Okay, so I'm going to use this bicycle pump to add some gas. Boom, boom, boom. Okay, now if I change different variables, the most important variables to think about with respect to this gas, or any gas for that matter, is the temperature that it's at, the pressure that it's under, and the volume of the container. So let's think about this. Let's watch the gas get heated up. What do you notice about the motion of those balls? Each one of them representing a gas molecule. The motion speeds up. What also happens to the number of collisions? They also go up. The number of collisions increase. Okay, so now let's, you know what, I'm going to go ahead and cool it back down. I'm going to cool it maybe cooler than it was to begin with. Okay. The motion decreases. The number of collisions decreases. And then if you look at this gauge up in the upper right-hand corner, you might notice that, well, the pressure is decreasing. So as I cool it down, the pressure decreases. Okay. Now, this shows the relationship between these different variables and how gases behave. If I were to, now let's go over to play around with the gas laws. So I'm going to add some gas to this container. Not too much. I'm going to add, yeah, there we go. 2 bursts of gas. If I were to change the container, and let's go ahead and, yeah, I'm going to adjust the shape of the container, shrink it down. Whenever I did that, or whenever I adjust the size of the container, if I increase it or decrease it, what happens to my pressure? Well, as the volume of my container increases, my pressure goes down. When I shrink the size of the container, my pressure goes up. And whenever you adjust and play around with these different variables, like increasing the size of the container, what happens to the number of collisions? Collisions go down. When we shrink the size of the container, well, the number of collisions go up, and with the number of collisions increasing, then the speed is going to increase. Now, if I reset it, 1, 2 pumps of this gas in there, I've got pressure at 11.7, and I'll talk about the units for that after a little while. If I increase it, what happens? I haven't changed my volume, but the motion has increased. The number of collisions has increased. So you could argue that if I am adjusting the temperature, that's similar to adjusting the size of the container. Meaning, if I increase the temperature, that's almost the same as if I decrease the volume of the container. Could you give me a W in the chat if, okay, I can kind of follow that, or a Z in the chat if, wait, I'm looking forward to learning more about this. Okay, great. Okay, a WZ, I respect that. Now, I'm going to switch back to my share. I'm going to add this link to the chat if you want to play around with it. And one of the things that I want to talk about with respect to gases is I think that gases and their behavior is something that's a little bit intuitive. And what I mean by that is there's something that you've probably seen and you've probably observed this before. Um, let's say hypothetically you got okay, here we go. I've got this vitamin bottle. And it has a volume in here. When I close the cap, then I'm kind of restricting it. The amount there is some gas in there after I close it off. Let's say I've emptied this out, I've taken all these vitamins, I close the cap, and then, and just so you guys see, opens, closes pretty easily. What do you think would happen if I got this container, I put it in the microwave, and let's say I just set it to heat for 10 minutes? And let's imagine that the plastic doesn't melt. Could anyone tell me what's going to happen to that container? The shape isn't going to change. Spoiler alert, I'm trying to direct you in a certain direction. What do you think is going to happen to the container? I'm adding heat to it. There are gas particles inside. It will heat up. The pressure inside will increase. Um, do you think that at some point it will spontaneously pop? It's going to expand? Yeah. So what I'm getting at is if you close a container and you heat it, at some point that container is either going to burst open or, the container is going to have a massive failure. So does everyone follow me that if you heat a closed container, the gas inside will kind of find a way to occupy more space? Give me a Y or an N if you follow that. Okay. Now, has anyone ever heated a closed container? Has anyone ever made microwave popcorn? If you've made microwave popcorn, you've heated a closed container. Because that container, it's a paper-ish bag, and it's got this little adhesive. As the kernels begin popping, they're going to take up more space. And at some point, when you pull that popcorn bag out of the microwave, let me ask you, is that adhesive that keeps the bag closed, is that still intact? Completely. Let me adjust that. Is it still completely intact? No, it's not. Because the kernels are now pieces of delightful, wonderful popcorn that take up more space, but also the air in there has expanded. The air in there expanded to the point that it ripped that adhesive. So this is one of those things where I always kind of think that you have some experience with gases, and everything that we're going to talk about today, I want you to try to think about your experience and relate something to these laws that we're going to talk about. Okay, so when it comes to gases, there are a couple of things that I want you to keep straight. One thing is we are interested in volume right here. We are interested in pressure right here. And we are interested in amount of gas. And we are interested in temperature of the gas, sorry. Now, what I want you to make sure that you notice is the specific identity of the gas. I'll just say doesn't matter. And what I mean by that is if I'm talking about hydrogen gas, or let's just say methane gas, CH4, or even water vapor, H2O, as a gas, I'm treating them kind of the same. Now, do all of these gases have different physical and chemical properties? They absolutely do. Hydrogen gas and methane gas, they're flammable. If you put those in an open flame, they're going to ignite. Water vapor? Nope, it better not ignite. Now, when it comes to temperature, one thing that we've got to think about is we are always going to use temperature in the units Kelvin. So what that means is whatever temperature you're shown, In degrees Celsius, you've got to add 273. So what that means is room temperature in degrees Celsius is about 25 degrees Celsius. That equates to about 76 degrees Fahrenheit. So kind of a nice interior or inside temperature. That's going to be 298. So anytime you see a practice problem that mentions temperature in degrees Celsius, add 273 to it. That will give you the temperature in units Kelvin. Volume is always going to be reported in liters. So 1 liter is equal to 1,000 milliliters. Therefore, 500 milliliters is equal to 0.5 liters. Amount of a gas is always going to be listed in moles because we're chemists and we talk about things in quantities like moles. So 1 mole of something is 6.02 times 10 to the 23rd particles. Most of the time with gas-related problems, we're talking about 3 moles of a gas or something of that nature, or 2.5 or zero point 0.5 moles of gas. Excuse me. Last but not least is pressure. Pressure is going to be measured in atmospheres. It might also, if you go out and look at if you have a bicycle or something like that, and I have a bike right here. Just a second. Okay. If you look on a bike tire or a car tire, you'll see units like either kilopascals or pascals or PSI. Okay, so how would you calculate the 3 moles of gas? 3 times 6.02 times 10 to the 23rd? Yep. Nice. Perfect. Great job, Kelly. That's absolutely right. But what I was getting at with respect to this is most of the time when you see a problem, it's going to be, well, how many moles of a gas are found at this temperature, this volume, and this so on, which I think as we get into the later questions, it will be a little bit more clear. But yes, that's absolutely right. Okay, so we've got our first poll question coming up, and it reads as such. What is 25 degrees Celsius in Kelvin units? Is it A, negative 248 Kelvin? Is it B, 25 Kelvin, C, 273, or D, 298? I'll give you guys about a minute on this one because it's running. We got 23 participants. Now we got more than that. Okay, and I'm going to work through this one. This prompts you, expect this sort of thing on an exam because this is just a nice, explicit, direct question. And what you need to know about this is that right there. This reports it in degrees Celsius, so you've got to adjust that by adding 273 equals 298. So D is our correct answer. I'm going to go ahead and end the poll there. We've got a bunch of poll questions today, so don't fret. Okay, next up is on our next page. Question number 2. Question number 2 reads pressure conversion. What is 2,200 kilopascals in atmospheric units? Oh boy. Oh boy. Is it A, 22 atmospheres, B, 100 atmospheres, C, 2,200, or D, 220,000 atmospheres? And I'm going to launch the poll question right now. So that is up. And to answer this one, well, we are going to look at this, and the way that I always like to set this up is I say, okay, well, my problem tells me I've got 2,200 kPa, and I'm looking for atmospheres as my units. And just so you don't get mixed up, because when we're talking about gases, we do use the unit atmospheres. Don't mistake that for the atmosphere, the upper atmosphere, but instead think about it as well, the atmosphere outside is pushing pressure, or it is exerting pressure. Now, I'm going to then take my conversion, which is 101.3 kPa. I'm going to put that on bottom because, well, I want these units to cancel out, and then I'm going to end up with 1 atm. So I've got 2200, and I'm going to divide that by 101.3, which it looks like quite a few of y'all were just like, well, that's 2200. I can divide that by 100, and I'm going to end up with pretty much 22. 2200 divided by 101.3 gives me 21.7. Our best answer is this 22 atmospheres. Okay, I'm going to go ahead and end the poll there. And now we are going to get into the weeds of talking about different gases. So, and relationships between different variables. So we've got a bunch of gas laws, and we will talk about those gas laws by first identifying them. Now, we're first going to be looking at a relationship between pressure and volume. Now, I've got this as a poll question, but this is really more of a discussion poll question. So I'm going to be going through it, and you can answer as you see fit or whenever you're ready. So the first thing is we've got to know what this law is called. This is known as Boyle's law. This basically connects or relates pressure and volume. What do you think will happen to pressure if we increase the volume at constant temperature? Okay, so what that means is that are we heating a sample up? No, we're not. But we're increasing the volume. So it's always helpful for me to give myself numbers. And I'll say, okay, well, here, I've got my vitamin bottle. And let's say that my vitamin bottle is 0.250 liters, 250 milliliters, or 0.250 liters. And let's say that I was able to like scale this up and just not adjust anything that's in here, but instead adjust the size of the container. Could everyone give me a Y if you follow my explanation? Okay. So let's say I just, I magically grow this bottle without opening it or anything like that. I'm going to grow it to, let's say, 2.50 liters. So I made it 10 times as large. Now think about the fixed temperature. Okay, temperature is not changing. But then also let's think about the amount of the gas. Okay, so here's my dots representing my gas molecules. Okay, I should have drawn that smaller. Now I'm going to draw it in my increased size. Did I change the number of gas molecules in this container? Give me a Y or an N in the chat. Did I change the number of gas molecules? I didn't. Okay. So let's just pick this one right here. This gas molecule, let's go ahead and draw it right there. And then this one. I want you to think about in this container, in the small container, how many, I'm not a gambling person, so I have trouble thinking about odds and quantifying them. But I'll just say, do you think that this molecule right here and this molecule right here will collide in the smaller container? Give me a Y if you think, yeah, they're likely to collide. And if no, I don't think they're ever going to collide. Okay, so why? We've got lots of yeses. So chances of them colliding is pretty high. Now, if we make the container larger, what do you think that's going to do for their numbers of collisions? Do you think their number of collisions will go up or their number of collisions will go down or their likelihood of collisions? Decrease the odds. Absolutely. Okay. So the chances that they collide will go down. I totally agree with that. Does everyone follow that explanation or follow that kind of rationale? Give me a Y if you follow the rationale and a M if no, I'm mixed up. Okay, so we have a decreased number of collisions. Now, just to kind of refresh this, when we were playing around with this container and we increased the pressure, did our number of collisions increase or did it decrease? When we increased the pressure, our number of collisions increased. So, what do you think that means? And based on looking at the poll question, you guys are right. If our pressure, or sorry, if our when we increase the volume, our pressure will decrease. So we're going with B there. Great. I'm going to close that poll question. Now, to illustrate that, if you've ever, let's go ahead. No, actually, I'm not going to. This is just a video that, what do you think happens to these marshmallows in this container when all the air is removed from it? They're going to expand. Now, if we look at this relationship right here, this is the way of kind of calculating it. So I'm going to open this question up in just a second. Here, what we have is our quantification of it, basically. This is poll question number 4. What happens to the volume when we double the pressure at constant temperature? Well, what happens to our volume when our pressure, okay, so our pressure here, pressure is force over area. So the amount of, like, when you press down on something, you're exerting pressure. You're increasing the pressure. What happens to our number of collisions? They go up. Now, I like to go ahead and give myself numbers here. So initially, right here, we've got a pressure of 1. The volume is, let's say it's 7 liters. That is equal to pressure 2. What happens to our volume? V2. Well, 1 times 7. And before I proceed, does everyone follow my numbers that I just kind of put together randomly? Give me a Y if you follow the numbers and N if you don't. So I'm saying that this container is 7 liters. Okay. Now, 1 times 7 gives me 7 is equal to 2 V2. Divide each side by 2, divide each side by 2. V2 equals 3.5. So our V2 right here, well, it got cut in half from V1, or our V1 got cut in half. So our volume is decreased. So when we double the pressure, when you increase pressure, volume goes down, and vice versa. So P and V, pressure goes up, volume goes down. When you increase the pressure, your volume decreases. Similarly, when volume goes up, pressure decreases. The formula for this is effectively P1 V1 equals P2 V2. Now, have we seen a formula similar to that when we talked about solutions and dilutions? And if so, could somebody add it to the chat? Spoiler alert, yes, we have. When we talked about solutions, we talked about C1 V1 equals C2 V2, where we took a concentrated solution and made a diluted solution. And I'm not trying to say, oh, well, those are the same thing. Instead, I'm just trying to show that the relationship between these substances, or the relationship between the initial and the final state, are similar when we talk about pressure and volume as when we talk about concentration and volume. Okay, now that is the first thing. I don't get the math. Why didn't we multiply? Okay, so what we're looking at here is, I'm going to go ahead and we actually did multiply. So This is our initial, I'm going to say initial container. That's got our P1, and then 7 liters was just a random number that I put together. That is our V1. So that's the volume of our container. Now, our P1 V1 is the same as 1 atmosphere times our V1, which is 7 liters. Then we're going to set that equal to our kind of final system, where 2 atmospheres, that is a pressure, that is our final pressure, that's our P2. What we're trying to basically solve for is, well, what's the volume of this container? Now, just so I can get kind of feedback, does this illustration right here at the bottom, does that make sense to you? Like when here we have a weight, and then over here we've got 2 times the weight. We didn't change the temperature of the system, but what happens to the size of that container? Does this make sense? Give me a Y or N if you follow the illustration. Okay. So then I've got my initial right here, and then this is our final system, where our P2 is 2 atmospheres. And I'm going to multiply that by V2 because I don't know the volume of my container. Then I'll do 1 atmosphere times 7 liters. I'm going to drop the units and just go with the number. 1 times 7 is 7. I'm going to set that equal to, well, my final situation, which is 2 V2. So I've got 2 V2 is equal to 7. Well, V2 is what I'm solving for, so I'm going to divide each side by 2. 7 divided by 2 is, well, 7 halves or 3.5. That is equal to V2. Awesome. Great. Okay. So just to sort of reflect on these, we've looked at the relationship between pressure and volume. And the relationship between pressure and volume is that, well, we use the term inversely related, meaning one goes up, the other goes down. So when pressure goes up, volume goes down. When volume goes up, pressure goes down. How does everyone feel? Give me a 1 if you follow and can visualize pressure and volume, and a 5 if I'm going to have to watch this again. And 2, 3, or 4 if you're like, might have to watch it again, but I feel pretty good about it. Okay, so I'm going to put a check mark by this. Now, the important thing about when we talk about pressure and volume, did we address temperature? Yeah. Temp doesn't change. That's an important takeaway from this. Temperature does not change when we're talking about pressure and volume. Okay, next up, we're going to talk about the relationship between volume and temperature. Okay, so if you think about when we talked about pressure and volume, we did bring up temperature and we said temperature does not change. Now, when we talk about volume and temperature, what do you think is going to happen to pressure? Constant. Perfect. The pressure is going to remain unchanged because we're talking about only 2 things. I'm happy that you guys are getting that. That's awesome. That is a very big step in understanding relationship between volume and temperature. In addition to that, just as a little bit of a preview, well, pressure and volume, that's Boyle's law. Volume and temperature, that's a specific law. The relationship between pressure and temperature is a different law, and then between volume and amount, is another law altogether. Okay, so the relationship between volume and temperature is illustrated by what's known as Charles's law. Last semester I jokingly referred to it as Chucky's law, and I was like, and I asked everyone in class, well, we need to know the specific names of the laws for the test or just how they're applied. That's a great question, and you know, my nice, Charles, I like it. So I got a private message. Do we need to know the names? Um, I have asked that in the past, but I'll tell you that it's kind of rare whenever I do. I know that that's not the most direct answer, but I would just say when you're going through and studying, I would be like, can I do the calculation? Yes. Do I know if it's an inverse relationship or a direct relationship? Yes, I do. Okay, who's that law named after? So I would put that information as a low priority. Um, does that help? Sorry. Yeah, I'd put it as a low priority. I would say that I've asked that question or about those maybe like in the past like 5 years, I've maybe asked it once. So does that answer your question? Okay, cool. Um, all right. Anyway, last semester I was like, yeah, I'm gonna call this Charles Chucky's Law. Ha ha ha. And I was like, is everyone cool with that? And there were like five people who immediately responded with no. And I was like, I didn't really think you'd have a strong opinion on that one way or another, but they did. I respect that. Okay, so Charles's law, relationship between volume and temperature because pressure is kept constant. This question is, what do you think will happen to the volume when we increase the temperature at constant pressure? This is kind of like that popcorn bag. Well, if our volume goes up, or sorry, if our temperature goes up, what do you think is going to happen to the volume? We've got either A, it will increase, B, it will decrease, or C, it will not change. Just as a little bit of a spoiler, you're going to see this question again with other laws. Yeah, it's not C. Something's going to change. So then the question is, okay, if you got, let's say, I always like to think about if you got, I have the closed container, but let's say that you got um, if you got a Ziploc bag or a balloon. Let's say that you were in a refrigerator. You inflated a balloon as much as possible. Okay? A refrigerator is like 4 degrees Celsius. You blew up the balloon as much as possible, then you walked outside and it's 103 degrees outside. What's going to happen to that balloon? Chances are that balloon's going to pop. This is, does anyone know who Tom Brady is? Give me a 7 in the chat if you're familiar, or give me a 12 in the chat if you're familiar with Tom Brady. Okay, I selected 12 because that's his sports number. Um, he was a quarterback for the New England Patriots for quite some time. Then he went down to Florida to retire for a little bit. Um, and he had a little bit of a controversy at one point in his career. And what was found was that his team they were releasing some of the air from the ball because it would make it easier to catch on cold days. And it was wonderfully called Deflategate, which, man, great name. At any rate, the point is that they said, "Oh, well, we never adjusted the pressure. We never adjusted the volume of the gas. Instead, whenever it's cold, well, the ball is going to deflate a little bit." And everyone was like, "Really? I don't know about that." The principle of their defense was true. If the temperature goes up, the volume goes up. Same thing, if the temperature goes down, the volume will go down. Okay, so the correct answer for this is to this question right here. What will happen if we increase the temperature? The volume will increase. I'm going to close this poll question and I'm going to show you this kind of from a perspective of the numbers. And what do the numbers look like? Well, when we look at this as a formula, effectively, this is our formula. V1 over T1 is equal to V2 over T2. This formula gives us a way of relating the volume of a container and the temperature that it's at, and how do we adjust it. Okay, the important thing about this sort of calculation is the units must be in Kelvin. Now, does anyone remember, and I talked about this early in the semester, so it's been a minute, the Kelvin scale? There was a term used for it that started with an A. Does anyone remember what that was? I'll give you a little bit more of a hint. AB. Absolute. Perfect. Awesome, Kelly. Awesome. The Kelvin scale is an absolute scale. What that means is that the lowest temperature, Kelvin, is zero. No matter how cold it is, no matter how far into the center of Antarctica you go, the lowest temperature on the Kelvin scale is going to be a positive number. Meanwhile, if you were to right now, let's say that you traveled to Winnipeg in Canada, that's still probably. If you traveled to, we'll go with Antarctica. If you went to Antarctica right now, give me a 7 in the chat if you think that it might be as cold as negative 20 degrees Celsius. 7 in the chat if you think it might be that cold. Yeah. Now, convert this to temperature in Kelvin. How do you do that? Well, you add 273. So it's 253 Kelvin. Does that make sense? Does everyone follow that? Okay. So when you're doing any calculation with these gas laws that bring up a temperature, you have to use Kelvin. Make that kind of muscle memory. When you see a negative temperature, add 273. So with that, let's think about a container. Let's think about this balloon right here. If this balloon had a volume of 1.7 liters, and let's say that this is at 10 degrees Celsius. And I'm not going to change the number, change it to Kelvin just to illustrate a point. And then we cooled it with liquid nitrogen. And let's say that our temperature was negative 5 degrees Celsius. Okay. Would somebody, without doing a calculation, make an estimation of the volume of this balloon? And I mean, heck, actually, would you agree that let's say the volume has gone from 1.7 liters to, let's say it's 200 milliliters or 0.2 liters? Could everyone give me a Y if they believe that as a number? Or if they're like, yeah, I can see that. Okay, great. Now, it's zero point 0.2 liters. Let's think about this and let's try plugging numbers in. So we've got our volume, V1 is 1.7 liters. T1 equals 10 degrees Celsius. Okay, now my T2 is my kind of final temperature. T2 is negative 5 degrees Celsius. Okay, so 1.7 divided by 10 equals X, the volume that I don't know, that I've estimated is 0.2 liters. That's my estimate. And then my T2 is negative 5. So looking at this formula, what is the problem that I'd run into with this number right here? I got a private message. Don't I have to convert to Kelvin? Yes, I do. I haven't converted to Kelvin because I want to illustrate the importance of it. Okay, so if I have this as a negative number, what is that going to do for my volume? Volume would have to be negative. Now, how could a volume be negative? Volume is like what space does something occupy? Yeah, you're right. It would make that's impossible. So, my point here is one of the reasons that you have to convert to Kelvin is because you cannot have a negative volume. Give me a 9 in the chat if you follow that. Follow that explanation. Okay. So I got a private message. Will we go over standard temperature and pressure? We've gone over it a little bit when we were talking about gases and moles that they occupy. We will go over it a little bit more later on. So for this, now we have to make that change. T1 is 283 Kelvin. T2 is, well, 273 plus -5. That would give me 268 Kelvin. Now, that zero point 0.2 liters, that was just an estimate. I was really just throwing that out there as everyone agrees that this is a positive value. But here we'll do the calculation. T1 is 1.7, or sorry, V1 is 1.7 liters, T2 is 283 Kelvin, and then T2 is 268. So what I'm going to do is I'm going to say 1.7 times 268, 1.7 times 268 is 455.6. I'm going to divide that by 283, which is going to give me my V2, my new volume, is 1.61 liters. So that 1.61 just goes to show that my estimation of 0.2 liters was a little bit dramatic. Okay, so this is our formula. V1 over T1 is equal to V2 over T2. So just to kind of rehash all of these again, we've got Boyle's law for pressure and volume, Charles's law for volume and temperature. Boyle's law says that when pressure goes up, volume goes down. Charles's law says that when volume goes up, temperature goes up, or vice versa. When temperature goes down, volume goes down. Now, our relationship between pressure and temperature. Could you go back to Charles's law formula for a second? Absolutely. So, if you think about this setup compared to the setup for Boyle's law, when you're multiplying the two variables by one another and you're equating those to the final state of those two, well, when you multiply them, that's your way of showing that they are inversely related. Whereas volume and temperature, we describe those as being directly related. So when pressure goes up, volume goes down. That's Boyle's law. When volume goes up, temperature goes up. Pressure and temperature. Okay. What do you think will happen? This is one of our last poll questions. What do you think will happen to the pressure when we increase the temperature at constant volume? So we are increasing the temperature. What's going to happen to the pressure? But the volume is fixed. Well, think about that as if you have a balloon and you're exerting force on it, you're putting pressure on it. Well, the Volume is constant, so the size of the balloon is not going to change. But what is going to happen is the number of collisions is going to increase. So we're going to see a formula like this. P1 over T1 is equal to P2 over T2. So if pressure goes up, what does that mean for temperature? And think about the structure of the equations. When you're dividing the variables by one another, that means they are directly related. When pressure goes up, temperature goes up. Now, our units for temperature, again, must be in Kelvin. So could you give me a 6 in the chat if you see the similarities or the parallels between this formula and I haven't even said what? Volume and temperature. Yeah, they're very similar. Now, I'm going to go ahead and give another kind of summary of these. I'm going to stop the poll because we've answered that question. I know. Somebody basically apologized. I figured you were going to say that. So don't worry about it. You're absolutely right. Okay, so this is what, oh yeah, and I did not mention the name, which again kind of contributes to how often do I ask about this. A relationship between pressure and temperature is Gay-Lussac's law. So I'm going to go with pressure and volume. Pressure and volume boils. When I was in high school, I remember my first chemistry teacher said, "You boil peas and vegetables." And I was like, okay, I don't, but I gotcha. Um, Charles's law and then Gay-Lussac. Okay. I, the way I like to kind of categorize these really inverse or direct. And then kind of give myself like a little bit of a summary. So pressure and volume. P goes up, P goes up, V goes down, vice versa. These are inversely related. Volume and temperature, directly related. Pressure and temperature, directly related. Charles's law says that when volume goes up, temperature goes up. When pressure, and Gay-Lussac says when pressure goes up, but volume is fixed, then temperature goes up. I think that it's also helpful to go ahead and kind of put together the equation. P1 V1 equals P2 V2. It was very helpful for me whenever I took this class to look at the equation and then think, okay, they are inversely related, therefore I'm multiplying. Volume and temperature. Okay, and then P1 over T1 equals P2 over T2. Now, the last law, the last kind of principle, is known as Avogadro's law or Avogadro's principle. And this says that there is a relationship between amount of a gas and um, volume that it occupies. And this one I think is maybe the most intuitive. And I'm just going to go ahead over here to this last poll question. I'm going to launch this poll question. Relationship between V volume and N amount of a gas, or number of moles. What happens to the volume when we double the amount of gas? Okay, let's think about this. I always like to think about like a water balloon. People are still answering C. It's never C, everyone. It's A or B. Kind of thought that that would make someone be like, oh, well, I'm gonna answer C. But maybe this will. Um, if you have a balloon, as is illustrated right here, okay, this person has stopped adding air to it. Now all of a sudden they're like, oh, I'm gonna add more air. What happens to the size of the balloon or the volume of the balloon? It goes up. When you add more air to it, when you add more water to a balloon, when you add more anything, that volume is going to increase. It doubles. Now, to go back and tackle this, volume and amount is Avogadro's. Could anyone tell me, is this an inverse or a direct relationship? Add it to the chat. Direct, absolutely. It's a relationship between V, volume, and N, amount. So when volume goes up, what does that mean happened to the amount of that substance? That also went up. And this gives us our formula, V1 over N1 equals V2 over N2. This I found to always be very helpful to kind of itemize out these different equations and relate the different things. This was most helpful for me whenever I took this class to say, okay, well, I'm going to basically visualize this. I'm going to write it out in my head as PV, VT, PT, and VN. I had that list like in my head, and then I just kind of went from, okay, the bottom three are direct. Okay. If I can remember direct, then I can think about, oh, D direct division. Got it. And P pressure and volume is inverse. And by that not being direct and not being division, I was like, okay, multiplication. Perfect. I always found that to be extremely helpful so that I could do these sorts of calculations. If I know this right here, if I put that on my note card and then made a little note like, okay, temperature must be Kelvin. Okay, that's going to help me out. And then the next thing, well, one atmosphere, that's my pressure, is 101.3 kilopascals. Okay, that's going to help me. And then 1 liter is equal to 1,000 milliliters. Okay, that's going to help me out. So this table right here, or this slide right here, if I were to recommend anything related to the individual gas laws, this is what I would put on my note card because it gives me all the formulas. And the more comfortable I am with it, the more easily I'm able to kind of do these calculations on the fly. Okay. Um, could you give me a number between 1 and 10? 1 being, hey, I feel pretty good about gases because I see the connections, but I also have kind of my own experience with like heating gases and everything like that. Um, 1 being that and 10 being, I'm lost. What's a gas? Add it to the chat. And I think that, oh man. Okay. Okay. Um, I think that it's helpful whenever you're going through these different formulas. I got a private message question. Will we go over the ideal gas law, PV equals nRT? Yes, we will. We'll talk about the ideal gas law and standard temperature and pressure. Not, don't think that it's, today is Thursday. I don't think that it's Tuesday, but I think next Thursday. I kind of wanted to space these things out a little bit. Um, so yes, we will. Now, with that, I think that it's helpful just to throw down some numbers and just kind of visualize it. And it's helpful for me personally, or it was most helpful for me to look at or look at something like this right here and just give myself a random number and say, okay, well, the volume of this is 2 liters. The volume of this is, I don't know. Well, it's greater than 2. Okay. How did I get from here to here? Well, she added more air. Whenever she was adding more air, that's adding more moles of that gas. Then this right here is a little bit tough. I always found the Gay-Lussac law to be a little bit challenging to imagine because if I think about a container like a balloon and I'm putting pressure on it, then there's part of me that's like, oh, but I'm changing the volume. So then I had to kind of like convince myself, okay, don't think about the volume changing, but when you're applying pressure, what's that going to do to the temperature? Then above that, volume and temperature, I always found this illustration with this right here, the liquid nitrogen, to be helpful. You add liquid nitrogen to or you take a balloon and you put it in the freezer, you put it in the refrigerator. It's going to shrink, it's going to get cold. What's going to happen to those gas molecules? They're going to slow down. The number of collisions is going to be fewer. That was always helpful for kind of illustrating the kinetic molecular theory or kinetic theory of gases. Okay, well, if there aren't any questions, I'm going to go ahead and stop my recording.